So okay, so what was next? Okay, so Nick kind of gave a bit of a description about some of the waveforms that we've been using. So these are waveforms from Andy and Thomas Yanko and Nick. So we basically have a catalog of nearly 20 waveforms, some of which are purely numerical, and a handful of which are basically hybridized with a analytic, either stationary ring down or a slowly varying kind of linear chirp. There's the characteristics of these waveforms, of the hybridized waveforms listed in that table there. So, you know, things like they vary between a totally stationary frequency and a 5% change in the initial frequency. And they cover the kind of 20 to 200 odd millisecond damping time for the, you know, the kind of post-merger ringing down here.
Sorry, how do you model the frequency change?
It's just linear. It's
In
just
time,
a
linear in time.
it's just a linear evolution, just to basically, you know, just to check that the algorithm is robust against the changing frequency, and it only cares about the power that's in the signal. So it's, you know, arguably you could come up with something more physical, but as a first approximation, I think it's quite reasonable for checking the robustness of the analysis.
Sorry, I have a naive question about, so that's purely numerical, that's the waveform you get from the simulation?
Yep.
And the hybridized with ring down, can you explain what that is?
Yeah, so that's basically the purely numerical waveform with a ring down stitched on. I think it's when the amplitude falls to about half the peak amplitude. So Andy stitched on the ring down at this part. So everything up to about here is exactly this inset that you probably can't see terribly well. And then the rest of it is just a simple analytic ring down.
So why don't you use the full numerical one that you have available?
Because the full numerical one is strongly damped from numerical damping. So it's to get a kind of upper bound on
But what is
a more
the
physical
typical
damping.
damping time for the numerical? So we can estimate that.
It's about 0.005 seconds from there.
Is there really? Is really so much depth? I thought you had longer trains.
I mean, so these are kind of obscured because I tried to make them a bit more visible, but this is 0.02 seconds from the peak of the in-spiral here.
You just detected it earlier.
Yeah. So the question is, why can't you have a longer numerical waveform? And the answer is because the waveform decays very rapidly because of numerical problems. So I'm surprised that it's so rapid, the decay. And if you go and use higher resolution, you surely can beat this.
Yeah, of course, but you cannot afford much more resolution. And I mean, it also depends a bit on the exact model, on the exact equation of state. And so you need to make some compromise.
I mean, it's a trade-off. If you want to have a really better accuracy in the numerical waveform, you need to run a simulation for months, right? And then you have just one model. But in this way, you reduce the accuracy. You have the initial amplitude to be correct, and then you can supplement it with the analytic. In this way, you can run 50 models at the same time and do statistics.
But in any case, you cannot run simulation for a second round.
Yeah, it will in any case not run.
No one has ever thought about doing so.
You need to do that anyway.
Yeah, exactly.
Well, the point is that right after the merger, there is a transit, and you want to stay away as much as possible from that transit, so that you have the asymptotic bar mode well defined to get that frequency right.
Well, certainly in the long simulation, it's totally going to be dominated by the many milliseconds of this very flexible ring-down. What
I'm trying to say is that if you look at the F2 frequency at right after the merger, you look at the F2 frequency, you know, at the end of the numerical, you will have two different values, and stitching an analytic prescription there will make a difference. Anyway, was a
Sure.
So could you tell me the mass of the binary?
Oh, sorry, it's a symmetric 1.35. Those ones are anyway. There are, I think, a handful in here that are higher total mass, but I think they were all symmetric. So this is basically the full catalog of waveforms, just to bombard you with some pictures. One thing that probably is worth highlighting in here in particular, we do have one that's a kind of our toy prompt collapse waveform. So it's basically just an in-spiral that stops. Since they're extracted in the quadrupole approximation, that normally or physically you would expect the black hole ring down on the end here, but we're not looking above 4 kilohertz in this analysis. So, and it's basically done in the frequency domain. So any black hole ring down here would be irrelevant as far as the data analysis is concerned. We only look, it would be a tiny bump over here somewhere. So you can see the kind of general morphology of these guys. Generally a very distinct kind of F2 peak, some hint of the F1 peak, and then the residual in-spiral power lower frequencies. And again, in the hybrid waveforms, the previous figure was this guy, where the frequency is stationary, so it's almost a delta function there, but where where it chirps and there is some frequency evolution, there's a slope at the side. So the point is really that we're exploring a pretty diverse range of frequency contents and waveform morphologies here, and the results are pretty robust across that. So this table just shows all of some various characteristics of these waveforms, just calculated kind of off the bat without doing any real analysis. So
I have a question
sorry.
about the previous transparency. So in some cases, when you go from the numerical to the hybrid, the peak structure is amplified, and
Yes.
in some cases, it looks like it's suppressed.
I'm not it's certainly amplified, if it's just the stationary
Yeah, I
ring
was
down on the
expecting
end.
that if you just had one F peak that was dominating the hybrid
Mhm.
waveform, it would amplify. But what am I doing wrong when I try to compare the second panel with this? Yeah, if I'm looking at the second panel of
Well,
the numerical.
So I guess this is stationary. These are both stationary, but this one's about 10 times shorter.
You're not creating these hybrid waveforms from these numerical waveforms, no?
Oh, are you not?
It does.
Yeah, it's stitched on.
So
But
there's
they're
a
not
one.
side by side
Yeah.
match.
Yeah.
Oh, sorry. Yeah.
More on the left than on the right.
Yeah, there's not a one-to-one mapping here.
And it looks
So
like
you
the
have a
scales-
lot more time.
And
with
and
the
these are
hybrid
logarithmic
waveform.
scales, whereas these are
the
linear.
scales are
So
different and different.
if you put these on linear scales, then you
Oh,
can't
okay,
see any
fine,
features at
fine.
all.
Sorry.
So the exponential decay of the amplitude, it's always the same, or do you choose different
So
decays for different models?
they were just computed from,
So
basically
this is based
tabulated
on
here.
what,
What Nick was talking about yesterday.
on the mass of the upper mass unit mass and radius
Yes.
of the upper mass unit star.
Okay. So yeah, again, these are just some tabulated, kind of interesting quantities. So as far as this study is concerned, I've just been taking everything above 1.5 kilohertz as post-merger. There is, of course, going to be some contribution from subdominant peaks, between 1 and 1.5 kilohertz, which we'll lose in this approach. But really, our goal is to kind of measure the F peak, which is pretty much always above 1.5. So I'm not terribly concerned about that for the purposes of this study. And it saves us some headaches with trying to attempt time domain windowing and assuming you know the time of the in-spiral. So it's a pretty conservative approach and estimates and so on. But the thing to highlight, I guess, is just the horizon distances that we get out for these waveforms based on just taking the computing the SNRs and rescaling to a kind of nominal SNR threshold of about 3, which I can justify. It's as appropriate for the kind of analysis we have in mind, and I'll say a bit more about that in a second. So it's a few tens of megaparsecs. I think there's one that goes up to 60 somewhere. Well, there should be. This column actually shows the expected detection rate, assuming the so-called realistic binary coalescence rate of, I think, 100 coalescences per Milky Way equivalent galaxy per mega year. So, obviously, I guess take that with as many pinches of salt as you want with the estimates of coalescence rates. And I guess one other thing to highlight here is these are just the energies in the gravitational waves above 1.5 kilohertz. So it's a few percent, and quite a lot in this hybrid guy.
What did you say was the total mass? Was 1.2, 1.2?
1.35, 1.35.
Okay, so
So
that's 1.2
So
So
these-
3%.
But that's in solar masses, huh?
I understand.
yeah, this
So
is not a
it's-
fraction of the
but the
total
top
binary
one
mass.
is about 3% of the total mass in just the peak. don't
So
understand these
that's
numbers.
everything above 1.5 kilohertz.
That's quite a lot.
Yeah.
Well, but you get 0.76.
Yeah, so what is, there are points there that seem to be,
That,
that can't be
so,
right.
it's solar mass. I don't understand these numbers at all.
They're just the usual.
Drastically high, 76%. Well, you divide that by, of course, 3 solar mass. It gives you 25% in
I mean, those are just
of
that's
the total
the.
mass in gravitational waves. I don't believe this number at all.
Okay, I will recheck them, but it's just the usual integration of the.
total mass.
Yeah, I mean, I was surprised, but that's
82. There's also 82 there.
Is that one of those very long lived
Yeah.
ones?
yeah, it's
I
one
think
of
that's
the.
artificial. I mean, you're just assuming that they will live forever or something. But and also very low damping. Can you go to that particular model? Let's say
which one was
0.76
it?
or 0.82, and go back and look at what is tau naught.
HL
That's
APR
what
dagger.
APR.
Yeah, it's gonna be a nightmare to see them on here.
The top one is,
No,
It
you
will
can
be
go
this
back to your
one.
table, right?
I think.
Ah, okay.
yeah, but the first and the third, I think, are some H1 APR of those two. Right?
Uh-huh. And the damping time is what I wanted to see, but maybe it's in the
Oh yeah,
previous table.
it's
you had
the
these.
it's 200
Yeah,
milliseconds.
So that's 200 milliseconds is the damping time.
And integrated
But it's a second,
over.
I mean, it's basically second.
I think we should emphasize here again what I mentioned yesterday, that these are two limits, and within these two limits, between around 20 milliseconds and 200 milliseconds, we expect that the real damping time would be. And we expect it to be more towards the, as we mentioned also in the paper, more towards the 20 than towards the 200. The 200 is a very simple estimate if you ignore completely the rotation of the star based on these empirical formulas that were constructed for non-rotating stars. And it starts there as an upper bound because we don't have the actual result. The 20 millisecond is based on the uniformly rotating stars, and it's closer to reality because you already have rotation there. It's just you're missing the differential rotation. And
Do you take okay, these are all numerical simulation, but what about radiation back reaction?
It's not in there. They are
They in the numerical
CFCs.
It is included, just in an approximate manner.
But not in the hybrid part.
No, not in the hybrid.
Yeah, that's what I mean.
But are there simple energy conservation arguments? I know that, when you drop a proton on a neutron star, you get roughly 20% of the binding energy. So that's the amount of energy available. So I would guess that no matter what you do, you can't, if you have if you have a 1.35 solar mass object and I just drop one proton at a time, I would get at most 0.25 solar masses in energy out. Now, in addition, this stuff is shock heating. A lot of this energy is going into
It goes to
neutrinos.
different things. It just
Exactly.
goes into.
So I'm suspecting that this 0.75 must violate energy conservation
Yeah,
at some very
this
basic
is
level.
certain. It's not there to show that maybe you get so much out.
Right.
It's
So
just
that means that
to
the
show that-
damping, there is an upper limit.
Yes.
There's a lower limit on the damping time scale that you can derive without really doing very much work.
Yes, yes. It just shows that this 200 milliseconds is unrealistic, and we need to do the real calculation.
Sure. Okay.
But how does this affect the horizon range? So should we simply take everything by a factor 10 smaller? Because you are.
There's only a couple that have
Yeah.
this.
Yeah, we can go back to that table, distances.
So these 50 megaparsec ranges are then the ones that are probably unrealistic, but there's other ones that are.
Yes, it's also interesting that there's such a large spread in the amount of energy being radiated between equations of state.
That immediately goes back to the damping time.
Yeah.
Yeah, a factor of 10.
Yeah, it's the hybrids that have the.
understandable, but it's just that there's no back reaction taken into account, and I know it's a very hand-wavy model, and I can almost get anything.
The corresponding spread in distance is only a factor of 2.
Sorry?
The corresponding spread in distances is only a factor of 2 compared to
That's because the square root of energy.
square root.
Yeah. So there may be a factor of 10 in energy, but that would be factor of 3 distance.
Shall I continue?
Okay. So it looks like maybe.
That's not surprising, is what I'm saying.
So the larger distances correspond to these unrealistically large EGWs. So maybe we should, for the purpose of this session, believe the ones with the smaller numbers.
Well, it's probably bigger than the smaller number,
Okay.
but it's.
Okay.
Closer to the
So
smaller.
why would it be bigger than the smaller number?
You were
Because
telling
we
me
know
my
that those are
first
strongly
one
numerically
thought
damped.
was-
Yeah, I think it's much less.
Or j-
No, but you said you don't, the damping, you study it analytically, you don't study numerically.
not so.
But there's also instances here that are just the straight
Yeah.
numerical signals, which are strongly damped.
So everything from down here has the this analytic hybrid stitched on the end. Everything above here is the pure numerical waveform.
I see. So you're not comparing the same things. In the one below are a time scale given by the damping time, the F mode
Right.
damping time, and up it's just a numerical window in which you carry out a simulation.
Yes. Yeah. So it's probably not terribly clear from this table, but the hybrids are kind of indicated with HL and HS, which it helps when the caption from the paper's there.
Should we expect the FP to change just because you hyperplace? So looking at the numbers in the last one.
Some of them will because it evolves.
Yeah.
So
It's a linear
yeah.
growth. Well, yeah, growth of time.
So there is a prescription used there.
Yeah, linear.
So the bottom line is, if we look at the first hybridized case, so the APR, there are two lines. The first one that has this 0.76 solar masses is the unrealistic one. And the second line, with 0.14, is the one that has a damping time scale of around 20 milliseconds. So 0.14 over the total mass, that gives you what Satya was asking yesterday. What is the energy in solar masses?
Right.
So it's a few percent in solar mass.
I see. Okay. So we got to take with caution the ones with 200 millisecond time scales. The others are all realistic.
Yes.
Discussing with you yesterday,
Yeah, I think
they concluded to be far lower.
I think that, I find it quite high, as I mentioned, but I don't know.
Have you observed shorter last time?
I mean, full GS simulation, I think it's much less. It's
Yeah.
electromagnetic fields.
But are you saying that it's less than 20 milliseconds, or are you just saying it's
So the simulation I'm referring is less. That it's a particular simulation of code and there's no INT.
For which equation was it?
It's one of the spectrums.
Oh, because the Shibata, for example, has published other simulations where, based on the angular momentum that is lost during the simulation, he estimates a gravitational-wave damping timescale between 30 and 50 milliseconds, which is close to our lower bound of 20. But it was not less than 20.
So we certainly have.
This was from.
Can I ask a more
And let me just say, we certainly have
Fundamental
more than
aspect.
25 milliseconds without problems, and in some cases, the amplitude shows a very little decay.
all I want to ask is, don't we expect in binary neutron stars less total energy than a similar system, same masses, for a black hole?
No, just for in spiral. That statement can only be
No,
applied
but
for in spiral.
in the case of neutron stars, there are all the dirty astrophysics which can take
No,
away
but
energy.
take a bar. Take a bar. You can use
Yes,
all of
I
your
agree.
rotational energy and convert it into.
I think that's
so-
right.
so-
You can radiate here. You can radiate the rotational energy that goes into differential rotation in the merger. In the black hole case, it doesn't exist.
So you don't have
So
that
you
limitation.
can gain quite a lot in this case.
The
In
fluid-
principle.
Yeah.
And the fluid is more
Principle, but there is this.
deformable than the horizon.
Yeah, well, I mean, the black hole ring down is very, very, very short and low amplitude compared to this.
That's correct, I agree. All I was saying was, I mean, there is a total amount of energy. I think Stephen Hawking computed it for black holes, 33% or something like that.
He's not good enough to calculate it for neutron stars.
Sorry, no, that's correct. He could have. No, all I'm saying is, what is it? Simply based on some energy or it's a true statement.
It's a true statement.
So I think what is an interesting estimate is convert all of your rotational energy. That should be the upper limit.
Yeah. Okay.
So just calculate I omega squared or J I, whatever, and then you know what is it that you can convert into rotational energy. It's going to be that's an upper limit because
I think you're stuck at this slide.
Let's
That
stay on
was-
this one. I feel happy with this. I feel comfortable and sort of warm inside.
Shall we? Okay, so I guess kind of more into my realm of expertise. So of course we don't have templates as such yet, really. I'll say some more about that towards the end, hopefully. So we basically end up having to use a kind of generic unmodeled burst search. I don't want to kind of overwhelm people with data analysis, but the basic idea is just to search for excess power in some time frequency plane instead of matched filtering. And the idea is to basically do it coherently or coincidentally between detectors. So in the algorithm that we use in this, coherent wave burst, what happens is that the data from multiple detectors is just decomposed with a multi-resolution wavelet basis, and then it carries out a coherent analysis, a coherent sum of the likelihood, which is maximized over all possible waveforms and sky locations. So it gives you basically a measure of detection confidence in basically the hotness, the heat of the loud pixels that you end up with in the time frequency maps. But one of the other, or perhaps one, the really nice thing that this gives you, as well as just detection, is it allows you to reconstruct the gravitational wave signal that's present in the detectors, basically without knowing what it looks like, other than it has to be coherent between detectors. So it does require multiple detectors. I'll say a bit more about that in a second. So assuming we find some significant excess power, and then the algorithm reconstructs the waveform, the extra bit that we added on in this analysis is basically to characterize the kind of post-merger scenario just by taking the PSD, the power spectrum of the reconstructed signal. There are more, I guess, informed things that you could do with this, but as a first approach, it actually works pretty well. So we modeled the kind of prompt collapse scenario to prompt collapse to a black hole. It's just a power law in the power spectrum. And then the delayed collapse, or the formation of a hypermassive neutron star, is a power law plus a Gaussian bump. And that lets us basically choose between those two models and recover F peak pretty accurately. So there's a cartoon of what's going on here. So I think I deliberately chose something like 0.5 megaparsec so that I got a ridiculously loud signal, just so that you can see what's going on here. So the left column shows the target waveform, so there's no noise there. The middle panels are the reconstructed detector responses for LIGO, Hanford, and Virgo. And then the right panel is basically an average of it's an SNR weighted average of the PSDs. And we choose between this power law plus a Gaussian bump and a power law. And it correctly identifies the post-merger scenario. We clearly have a post-merger signal here. And then the prompt collapse example with a slightly artificial in-spiral only guy is of course essentially just a power law decay. And again, the red curve is meant to highlight the thing it's chosen as the best fitting model. The fitting is basically done using this thing, the Bayesian information criterion, which is a slightly fancy chi-squared fit. So in principle, it works. We can measure the peak frequency and we can choose between post-merger scenarios. So the obvious question is, how well does it work? So basically, we took the 20-odd merger waveforms and threw them at some recolored initial LIGO and Virgo data. So it's data from S5 and VSR2, recolored to have the sensitivity expected for around about 2020 odd. So it's the zero detuned high power curve for advanced LIGO and a similar curve for Virgo actually. And then the kind of detectability figures of merit are fairly standard in the gravitational wave analysis literature. We compute a kind of an effective range for the search, and then for quoting the results here, it's kind of interesting to compare with the literature if we just convert that to a horizon distance with the scaling shown there. And of course, then we compare the range that we get from the burst search with the totally idealized optimal matched filter strategy. So another fairly conservative thing that we adopted for this aspect was basically to require basically a 3 sigma significance for detection after imagining that we've followed up order 100 binary in-spiral events. So taking that trials factor into account there. Now that may be optimistic in the the sense that there may not be 100 events in 1 year to follow up, but it's it's pretty conservative to give us our thresholds. And that all works out to give us an SNR of about 3 for the optimal search. And it's empirically measured for the burst search.
Is that significance, is that just detection or non-detection?
Yeah. Well, it's the significance of it not being noise. So
you could probably
could lower that.
And do you know do you have an idea, say, if you're saying, okay, we're doing astrophysics, we just want our best guess, like how does the horizon increase if you lowered the significance requirement?
I don't have an intuition for that. I'd have to run the numbers. It would be easy. Yeah. So these are the the kind of detectability results again. So hopefully this makes a bit more sense now. As we discussed, you can take these particularly large distances with a bit of a pinch of salt. But you see there's some deficiency between the difference between the totally theoretical, what you could achieve if you knew everything, and the burst search, which is pretty much expected. You could see that as disappointing. I see it as an opportunity. The other fun thing that you can see is that the classification kind of algorithm, so choosing between prompt collapse and either delayed or stable post-merger objects, is pretty good. Most of the time it works better than 95% or so. This is averaged over all the found signals. There are some guys that are somewhat harder to classify, and basically what's happening here is that the post-merger peak in the power spectrum is at much higher frequency. It's harder to reconstruct. So those are, in some sense, misclassified. But it turns out that had we not applied the model selection procedure, then we'd be trying to measure the peak frequency for something that we can't see, and you get the peak frequency quite dramatically wrong in that case.
Is this done in real data?
It's recolored S5 data, yeah. So it's recolored S5 data at high frequencies, so it's pretty Gaussian.
Yeah.
What do you mean? I probably missed a little bit. Classification accuracy, 0 to 1?
So this is basically the probability of correctly identifying whether it's collapsed to a black hole or formed a post-merger neutron star.
Which is the fake collapse one?
This guy,
So that.
the high mass SFHO. So yeah, it works just as well for prompt collapse as delayed.
Why that model, that mass?
It collapsed, I think is basically.
It's a very soft equation of state. I mean, you know it truly. And if you have two stars with 1.6 solar mass, it collapses.
Oh, okay. And so the NL. Oh, I see. So the NL 3.8, did that also collapse or no?
I don't think so. I think.
No, because that has a higher radius.
Yeah.
Yeah. Okay.
So your basic information criteria thing is between those models and.
It's between. I don't know if this will show up, but that's our surviving post-merger object. That's our black hole. And in fact, this sometimes there's not really kind of residual in-spiral power here. This part of the template, if you want to call it that, is doing a nice job of picking up the subdominant peak.
No, I was
But
just confused whether you were doing those models compared to that prompt collapse model.
No, they're just power law plus a Gaussian or a power law. The point is that most of the time we do a pretty good job of distinguishing post-merger scenarios. So put another way, if you even when you do have prompt collapse, without any further data conditioning like windowing, you will get residual power from the in-spiral within the search band. So it's important to do that model selection test. So then the final stage, penultimate stage, is basically to try and recover the peak frequency, because that's the thing that we want to do astrophysics with. So this is just a box plot showing the absolute error in the recovered peak frequency when we do this fitting procedure. Our estimator of the frequency is the location of that Gaussian. So these are the different equations of state used. Obviously doesn't feature the prompt collapse waveform here. So the red line is just the median. The boxes show the kind of interquartile range across all the Monte Carlo simulations, or the entire Monte Carlo simulation. The red line's the median. In the
median error.
Median absolute error. Yeah. So it's around about 10, 20 hertz. Obviously, for the the stationary hybrids, it's much smaller because it's such a well-defined peak that massively dominates the SNR in the signal.
That's in your paper?
Yeah.
So all of these guys have the same signal-to-noise ratio?
No, this is averaged over everything that's found.
Okay.
So.
Do you ever see observation forecast low frequency side rather than center of error, but red or right aligned to lower frequency side?
This is absolute error.
Yeah.
What do you absolute error?
Like the difference in the recovered frequency from your two.
Yes, I understand it. So quarter, I think. For all the models, the red line comes the left half of error. So is there
Oh, it's asymmetric, you mean?
It's the median. Could be median.
It's a quantity that you expect to be near zero.
Yeah.
It's never going to be in a
Medians are always,
What?
You know,
It's the
smaller than that.
Gaussian.
Scale effect, yeah.
But because, yeah, because it's cut off from zero.
So you want this to be zero, but of course, there's also the fact that these peaks are sometimes somewhat asymmetric, and particularly in, who knows what the reconstructed peak actually looks like. But this guy, for example, I'm trying to fit a Gaussian to this, so there will be some systematic bias in that, so that would probably also explain it. But it's, it's still small. So as we heard, I think yesterday morning, Andy and I think various people now have come up with or spotted that there are these nice relationships between the dominant post-merger peak frequency and the characteristics of various fiducial stars. So this just shows the the relationship between the measured F peak and the radius of 1.6 non-rotating cold reference star. So the idea is that if you can measure this peak frequency, and you can map it back to the radius. This relationship in particular is it's specifically for symmetric 1.35, 1.35 system. Other relationships will exist for different masses. I think it's fair to say that we'll know the masses with some reasonable accuracy from the in-spiral phase. So it's just a case of forming the relationships for the different masses and measuring that from the in-spiral. So this is what happens when we plug the peak frequencies into that relationship. Basically, it's the same style of plot again. It's the absolute error in the radius for these equations of state. And it's around about 100 to 200 meters, which is pretty tight.
So this is for that mass or for any generic mass?
So it's for that mass. These are restricted to those masses.
This is related to my previous question. You tend to overestimate the radius.
Mm-hmm. Yeah, there are some subtleties here because of the, this relationship. It's got this knee in it. So if you get the peak frequency wrong by a few hertz, then you can go into completely the wrong regime. So there can be some large error bars on some of these guys, but
I think it's systematic from your Gaussian fit to that particular shape that's
mm-hmm.
tilted to the right. I don't know which way you'd say it's tilted. Drifting to the right, you're going to always overestimate the frequency of that. Yeah.
Mm-hmm.
You get because shifting or you expose or not.
Sorry, how do you see the biases towards one side?
So on the shape of that feature in a lot of those in the waveforms was steeper on the left-hand side, so that say the panel, the first purely numerical panel, so steeper on the left and goes to the right. You're trying to fit a Gaussian into that. You're going to always overestimate the peak for those systematically. But that's not a massive problem. You just add an extra parameter to your model that you fit in the future.
I mean, we're already doing, getting it to tens of hertz, 100 meters or so. This is the thing runs in minutes. The fitting procedure runs in seconds. It didn't take an awful lot of work to bolt that stuff on the end. There's lots of enhancements. This is just the beginning. So finally, this kind of token summary slide. So yeah, the point is it's a kind of first systematic study of detectability of these signals in kind of realistic data. It's, the data is slightly non-stationary. It's got gaps in principle. There were glitches, although I don't think they actually affected the analysis at all. You kind of see that there is a disparity between what's theoretically achievable and what's actually achieved in real data with a real algorithm. So there's lots more to do. But despite that, we already do reasonably well. We can see to 10, 20 megaparsecs, which we obviously want to see further. And this extra stuff with the model selection and the frequency estimation actually works. It's very simple and it works really, really well. So to conclude, there are some things to move forward, at least from the analysis side. There's clearly a lot to think about from the the kind of numerical side as well. But really, the idea is that the study's meant to kind of set the bounds for what we could do tomorrow if the network suddenly switched on and we started seeing things, versus what's theoretically achievable. So just this week and the past few weeks, months, there are lots of different ideas and obvious extensions and totally different analyses that you can do. In particular, the thing that I would really want to do is some fully Bayesian analysis to recover the posterior on R1.6, essentially. That's going to be the thing that you want to use with, say, in-spiral measurements to better constrain the equation of state on like a mass radius diagram. And I'm not going to read all this out, but I've been playing around in just the past few days. You can actually get a long way with a totally ad hoc, simple, kind of damped sinusoid template. It's in quite high overlaps with these numerical signals. So that's quite promising, and there are all sorts of advances and extensions that one can do. So I think I've probably taken up plenty of time. Thank you.
Questions here?
So if you put a binary at 10 megaparsec, how does this radius determine if you compare with the one from today's inspired?
I think it's about the same. I think I was talking with Jocelyn yesterday. I think you expect to get the radius to about a kilometer at 100 megaparsecs optimal from the in-spiral phase, so we can get 10 times closer.
Actually, it can be a third that if you assume you have perfect waveform modeling for the in-spiral. The plus or minus a kilometer at 100 megaparsecs is just this sort of numerical only matching. So that would be a sort of similar. So you get plus or minus a kilometer at 100 megaparsecs. So at 2 megaparsecs you get 100 meters, which is comparable and maybe better if you get rid of somehow these higher order PN style mathematics.
But they're very complementary. They probe different regions of parameter space in the mass radius diagram. So it would be amazing to have both. 2 points on the.
You're talking about, that was talking about radius, you're saying the mass radius plane putting blobs on that. They may be orthogonal. Do you know?
So you're effectively measuring the radius of a much more massive star compared to the one. So
Yeah.
you're making 2 radius measurements.
Oh, okay.
You're making
At different masses.
So it's really impressive that you can get basically 10 hertz measurement of this peak.
Frequency is pretty easy to measure.
Higher the frequency you go, the better you can determine. That's okay. But I do worry that those energies are the ones that you need to worry about.
Sure.
And when you include those more realistic ones, these estimates might be a factor of 3.
But this
Maybe
did
not.
include lots of the realistic.
Yeah.
Sorry?
This did include the realistic ones. There were just a couple of them that were those extreme cases.
So if you just use the
I
numerical.
don't know whether
data-
all of them go down by the same factor. That's what I mean.
But some of them are the numerical.
Yeah, the purely numerical ones you can take as a lower bound, I think.
So if you go back to your error budget,
This one or the table?
so which are the hybrids are the ones at the top?
Yeah.
And all the rest they are systematic.
The point is, you could have made a similarly convincing case without ever talking about the hybrids.
Well, the hybrids, yeah.
Like 20 hertz, I would say.
Yeah.
the hybrids do let you see further.
Yeah.
So.
The distances increase the rate
Mhm. Yeah.
You had a slide out there with rates, though, the second to last.
Oh, yeah, sorry. I shouldn't have skipped over that, really.
I have dumb questions, because first of all, let's just assume that you get some information from the inspiral part first. That's going to be, you're going to know the masses. Does that go into information you go into estimating anything from the first part? Do you have to use that information at all?
It's a very weak constraint on the smallest peak frequency that we look for. You know, I think, I can't remember which way around it goes. I think you can, I'll need to check the paper actually and follow up on that. But yeah, you do use that information, but it's not critical.
The BNS rate given in that table is like what's called the...
It's the realistic one.
Realistic, right.
So yeah, we have to get lucky.
But if you have just one number for that rate, why do you have such a big range on the events? So,
That's the range and distance for the different waveforms.
right.
So you assume that you're not looking at the inspiral at all for this?
So for the burst analysis, what's assumed is that you know the time of coalescence to 100 milliseconds, which is, I think, very conservative for an SNR 100 signal.
I mean, in principle, I mean, you will see the inspiral first, and so you'll be able to see these out to like 100 or 200 megaparsecs. Do you know then, like, I mean, if you're not trying to do the detection problem with the merger part, I mean, you're assuming you already see it, does that mean if you see it at 100 megaparsecs, does that mean the area in the frequency is 10 times larger than if you see it at...
Yeah, I don't know how that scales.
Yeah, like maybe so you don't require this 3 sigma significance, then your horizon goes out further, but then of course all your parameter estimations would get a lot.
That'll get messier, and it's not clear how it will get messier because you'll start, you know, the reconstruction will just get messy. You know, if you...
It might be worth doing for like a 100 megaparsec kind of closeness signal, just to say this is the information that is or is not available.
I think the spectral analysis in Chris and Sathu and Luciano's paper is ideally suited for this. You don't have to assume.
No, you don't have to do spectral analysis, because what we were discussing earlier this afternoon, you could use the same template all the way up to, use the best model, EOB or whatever it is that is available, up to the end of inspiral.
Okay.
That's a coherent analysis, you got some result there. And then it immediately tells you within what time window F2 should be.
Right.
Very tightly.
So.
And use another template as such there, if you wish.
Yeah. Yeah, that's...
And then the both are...
Is that not what I was...
you could use, sorry?
Surely that's, I mean, that's telling you the time of coalescence, and that's the information that I'm using for the burst search, or, you know, it's the information that you would use, yeah.
Yeah, but you could combine the two, and you will get a lot more, because you can get the equation of state information from the earlier inspiral part as well. And you combine that, you can use one of them as a triad.
But that's this idea we were talking about, that there are constraints at different sort of effective masses, so you get multiple constraints on sort of effective mass radius plane or whatever you're using.
That's right, yeah. They use.
But they'd be fairly independent analyses that you would then combine afterwards to see.
Yeah, that's right. It's independent, but both can be coherent is what I'm saying. It don't have to necessarily look for spectral. We did a spectral way of doing these things because we were doing both F1 and F2. And if you combine the two, you can't use a coherent approach because we don't know the signal model all across. But if you're doing only one of them,
I see what
you're doing, right? You're doing only F2. You don't need to do spectrum.
Well, actually, I think you could do a fully coherent thing with a superposition of 2 ring downs. You know, you have a lower F1 and a higher F2, and then just sum them.
In a spectral method.
No, you could do it fully coherently.
Except if you have the waveform model,
Yeah.
that's what we want, but.
I think.
Can't you use two Gaussians?
We do that.
Yeah.
We do Gaussian things.
We use something a bit uglier.
That's right.
And that's, you mentioned what we do. I mean,
Yeah.
it's incredibly similar to what you do, except ours is an uglier model. And I was going to say.
I don't know. I mean, you work directly with the data. I work with the reconstruction from the burst searches.
Well, what I was going to say is this hybrid thing, which may have issues, but that would be a nice thing to use as a template. If the F2 is the thing that you're looking for, and you can accurately model that as this ring down.
Yeah.
Just parameterize, that's a 2-parameter model. Frequency and decay time.
Yeah.
And do that as a search, and you get exactly that asymmetric shape.
Did you say that something with the actual line size is a conflict?
So I was going to hold this back because it's not. It's a bit preliminary. But so I was just playing around with basically technically it's a damped chirp with a kind of cheeky window rise. So the top ones, I think that's a Shannon equation of state waveform. It's just the raw unconditioned data. Here I high pass and window it, as similar to you, which of course requires knowing the time of coalescence. So I was initially scared of doing that. And then it turns out that with very little tweaking, I get a match of like 87%. So, just adding a few more parameters, thinking a bit harder about this.
How do you get a match? Is these
So the noise weighted in
with frequency change or?
Yeah, the frequency change is allowed, but in this case it's actually unnecessary. It's quite stationary.
So that sort of implies that you could get, so your first search is giving you something between a third and a half the optimal distance, but if you have a match with 0.87, you'd get
You can get much further.
0.87 of the optimal distance. So
Assuming,
you back up around 50.
you do everything coherently and so on. And of course, all those optimal estimates assume known sky location and time and things, so there'll be some loss from that.
When you say coherently, what does that mean? Is that
Combining data streams.
Sorry?
Multiple data streams, complex.
So coherent between detectors?
Yes.
Right. Can't remember what we did.
For your frequency accuracies, were you assuming data from all three interferometers, Hanford, Livingston, and Virgo?
Yeah.
How essential is it for all three interferometers to be there, and how worse would it be for the two interferometers? Let's say just Hanford, Livingston, which are of course not completely aligned.
I don't know, but I would guess it would be like the square root of the reduction in the number of detectors. If your sensitivity is.
But there could be degeneracies, right? Which you may not be able to break.
What do you mean? You mean because of the sky location and polarization? What do you mean?
So, right. Yeah, about, okay, so the distance polarization.
For this particular one, you don't need to bother about.
So what is, I'm trying to understand, what are you gaining from this, the coherence for this one?